determination of the ideal gas law constant, R. So we talked about R in lecture yesterday. Basically, R is the constant. It's a number that remains the same, that basically relates all the other things we measure in terms of gases. Relates pressure, volume, moles, and temperature. Relates all those four things into a fairly straightforward and simple equation that brings everything together. So that if we can measure any three of those things, we can automatically determine the fourth. So the experiment today is going to be pretty straightforward. You're just going to be in a lot similar to the experiments we did in the last lab, where we basically just looked at the relationships between volume and temperature. That's really all we're going to do today. Is just change the temperature and note the volume. That's it. But we are going to also use the moles of gas that we're using and the pressure. We're going to have to work at a constant pressure, because remember, since there's four things we're dealing with gases, if you want to see the relationship between any two of them, the other two have to be held constant, or we won't know what the direct effects of those first two things are. So that's what we're going to do today. We're going to use a constant amount of gas. So N for moles will be the same. We're going to use a constant pressure. So the pressure will remain the same. The only things changing will be the temperature and the volume. So you guys are probably familiar with the background, because you actually investigated these laws last week and saw all the connections. You saw that there was a direct connection between some things and an indirect connection between some others. And so when we put them together, we got this really nice PV equals nRT expression, which unites everything together. So we were aware of what P stood for pressure, and V stood for volume, and N stood for moles, and T stood for temperature. But what is this R thing? And because we're dealing with four different values, with four different units, R is a fairly complex number in that it has four units in it. And so we have to be really careful when we're determining R, that we take all of those units into account. I mean, I've been harping on you guys for weeks and weeks and weeks now about when you do a conversion from one unit to another unit, always keep those actual units in the mathematics you're doing. Because if you don't, you may wind up flipping some things. You may have some numerators and denominators flipped around. And so you come out with a wildly wrong answer. That's going to be super critical today. Since basically what we're going to be plotting is an X and a Y, which will give us a slope that will give us the value of R. And so when we plot that, we're going to have to think really carefully about what units we're using, what units go on Y, what units go on X, so that when we look at the slope of the line, it's going to give us the proper units. And we'll discuss that while we're doing it. I sort of gave some basic information on how to do lab reports. It's just a reminder, basically, because on this particular set of instructions, there's not a lot of room to actually fill in everything you need. So basically, you'll just have to write it out yourself. So give us a heading, the title, name, the purpose, just really, really briefly, what the hell are we doing this for? Oh, we're solving for R. Okay. The procedure. Now, don't give the whole procedure. Just summarize it very briefly. 4 or 5 lines is really all you need. You have to go through every single small step, but sort of the broad strokes. When we get to the web page, this is the sort of the description here of how the experiment works, or basically why the experiment works. So what you're going to do is, here's what the opening screen is going to look like. And so what we're going to do is we're going to select a gas, and we've got 5 different ones to choose from. You're going to do 3 of them. So pick a gas, and there's a chamber there at the bottom, a piston, a cylinder. So we're going to put some amount of gas in the cylinder. That's the second slider there. You can see there's mass, and you go anywhere from 100 milligrams to 200 milligrams. Notice the mass is in grams. It's not going to be in moles. You're going to have to deal with changing that. And then we're going to select a pressure. Now, the lower the pressure you select, the bigger the volume is going to be. And we know that's the case, right? Because we did the experiments showing the inverse relationship between pressure and volume. So if we choose a really low pressure, the volume is going to be much bigger. So you can decide if you want to look for large changes in volume or small changes in volume. Larger changes in volume will give you a graph that has a greater spread on it. Large pressure will sort of give very, very small changes in pressure. So I would probably recommend a relatively low pressure. And then what we're going to do is vary the temperature with the third slider and see the effect of changing the temperature on the volume. Now, what the particular website, the simulation, will allow you to do is to actually, it'll give you a plot, basically to show you how many points you've done so far, and show you basically what the relationship is. What I would suggest is that you have a notebook or a piece of paper or something in front of you and write all of this down as you're collecting it, and we'll go through that. You select a pressure, a mass, a temperature, and then you hit calculate, and then it'll show you, basically, let me write on this a little bit. Draw. So what it will show you when you hit, oh, a little wider than that. When you hit calculate, it'll then give you a precise volume. So again, the temperature is not going to be in the proper units for you to do the calculations and the plotting. So take a note of that, because what units for temperature do we always use when we're dealing with gases?
Kelvin?
Kelvin, yeah, we certainly do. Since pressure is based on movement of molecules, movement don't stop till we get all the way to 0, absolute 0. And so we want to look at the change in Kelvin. So we're going to have to change our temperatures to Kelvin. They're in Celsius right now. So we're going to have to take degrees Celsius and then convert that to Kelvin. So we'll make a note of the pressure we're using. We make a note of the mass we're using, and those will stay constant. As I mentioned to death, we're looking at 4 different things going on. If we want to look at any 2 of them, we got to keep the other 2 in the background, staying constant, not changing. So we're going to be looking at the relationship between temperature and volume. And since the other 2 are going to be held constant, when we plot our data, we should be able to see the relationship between all 4 things happening at once. And if we see the relationship between all 4 things happening at once, that basically will give us the value of R, because R is the thing that relates all 4 temperature, pressure, volume, moles together. So let me clear that and move this over. All right, so we'll select a gas. We can just start with nitrogen. It's probably not a bad place to start. Introduce a specific mass, select a pressure, start with like a low temperature and just sort of move our way up, and it'll calculate what the volumes are. So a point gets plotted on the graph, and here's basically what your data will look like after you have picked at least 6. I mean, since the acquisition of data is going to be so simple, I mean, the more points you pick, the better your data is going to be. So, but at least 6 different temperatures. You can do 8, you can do 10, you can do 15 if you want. Because since, the computer is going to be doing all the calculations, take a lot of data points if you like. And so here we have done, let's see how many points we've done. 1, 2, 3, 4, 5, 6, 7. So 8. So we've got 8 different volumes from 8 different temperatures, ranging from, I think 1 is the lowest, 1 degree C is the lowest, and 250 degrees C is the highest. And so you can see the variation in volume from there. So, and that's basically it. That's the whole experiment. So you're going to do it for nitrogen, oxygen, or argon, and then you're going to do it for carbon dioxide and xenon last. So 3 different gases. You can pick different pressures, and you can pick different masses. In fact, I would recommend, I recommend doing different pressures and different masses, and get your data, and we're going to put them all in a data table that looks like this. So they're the 4 different things you're going to be collecting. So you're going to be varying the temperature, you're going to be seeing the volume. Moles should stay constant, so it should be the same all the way down. Pressure should stay constant all the way down. But the question is, can you just plot, is this plot good enough, basically, up here? The one that the computer supplies. This plot here, of just temperature versus volume. Is this going to give you, when we plot this, we did that on the computer, is that going to give you the value of R? Think about what the units of R, what are they? And so if I plot, so remember, what is the slope of this line? When we calculate the slope of a line, what does it actually give us? Those of you who've taken math, step in and help me out. What's the actual slope of a line? If I plot volume, so my Y is my volume, and my X is my temperature. What's the slope of the line? So Y equals mx plus b. What's m?
M is the slope.
Mm-hmm. How do I define it, though? So like Y is volume in liters, and T is temperature in Celsius. What would M be? What would the units of M be?
No unit?
Oh no, it has units. Yeah, if your y-axis has units and your x-axis has units, your slope is going to have units.
The unit of y over the unit of x-axis.
That's right, because basically M
Is
is just
y different between y over different?
is the change in y over the change of x. That's the very definition of the slope of a line. It's how y changes versus how x changes. And so, if that is the case, let me erase some of this stuff. If that's the case, then the slope of my line, if this is in liters, and you can see that it is, and this is in degrees C, and you can see that it is, and my M is delta Y over delta X, then the units of M are going to be liters degrees Celsius. That's going to be the units, because basically what the slope tells you is that if I plug in a value for delta C, for delta temperature, basically a temperature, any temperature. I can pick any temperature between 0 and 250. And I can use this number to convert it to liters, right? So I'll take my liters, I'll take my temperature. Here's my temperature. And I'll multiply it by the slope, which is liters degrees C. And when I do that, it'll give me liters. So my degrees C will cancel out and I'll get liters. And that's what the slope does for us, because it tells us the relationship between my X and my Y. So once I have that slope, I can take any X, if it's a line, I can take any X, plug it into the slope, and it'll tell me what Y is. That's the whole point of the slope. But will that slope will that be the value of R? Will M equal R?
No.
How come? Why not? You seem pretty positive about it. I appreciate that. You tell me why you think that way. Why are you so sure that it won't give you the value of R? Let me say I agree with you. I just want you to tell me why you think so.
Should automatically give you the R squared.
It should give you one. How will we know when we do when we plot some combination of data on X and Y? How will we know when we actually have the value of R in our slope? How will we know that?
When you do the graph, right?
Mm-hmm.
Wouldn't that give it to you automatically after you?
Yeah, I mean, we'll graph it, we'll get a slope, but how will we know that that's the number we're looking for? We have to have some way to figure out that, yeah, when we get the slope of this line, that's R. So you're correct in like this particular line of temperature versus volume doesn't give us R. But when we work out a combination that does give us R, how are we going to know?
You plug it in the equation.
Okay, yeah, we'll plug it into the equation, but I'm sort of just basically looking for how are we going to, even if we get a value that sort of looks like R, how are we going to know that's right? I mean, even if we get a number that, okay, yeah, that vaguely looks like R, how are we going to know that that's we're on the right track? I mean, we know that this isn't right, one reason is it gives us the wrong units for our slope, right? So the slope of the line in this particular instance, let me clear this out. The slope of this particular line is going to be, so it's y, since it's y over x, we're going to get liters over degree C. And we know that, well, the units of R aren't liters degree C. So this line is not going to give us what we're looking for. So we're going to have to, do some calculations, some permutations, move some things around. How will we know that when we've plotted the line, that slope equals R? What's going to tell us that, yeah, that's R, that's what we're looking for?
The points on the graph.
The value of, let's see what is it here. The numbers, the real numbers.
Yeah, I mean, but these are numbers. I got a line, I got numbers. How am I going to know I've got the right numbers and the right slope?
Is it the endpoint will fit into should equal the difference in the slope?
The values of R is close to 1.
The value of R won't be close. Oh, R squared. You mean R squared? That tells us how close the lines are, how close the points are to the line? No,
Yeah,
this looks really good. That looks straight to me. So that just tells us we have a straight line. It doesn't tell us we have the proper straight line. See, what I'm looking for is that what I said a minute ago was that we know that this line doesn't give us the proper value of R because the units are wrong. R is not in units of liters over degrees C. So how will we know when we have the right slope that gives us a value of R? Let's sort of chew on that for a minute. We're going to have to plot something else that when we look at this, at y over x, it's going to give us R. If these are the wrong units, how are we going to get the right ones? That's why I sort of want this lab to be a bit of a head scratcher.
Is there a certain formula that you have to use?
Yeah, I feel bad for the folks who didn't take algebra. This whole chapter is algebra, basically. So if you suck at algebra, this is not going to be fun. But if you liked algebra, like some nerds, it's fun, just like, twisting, moving things around. So basically what I'm getting at is I have to have the right units on the X and Y axis in order for when I do my plot, it'll give me the value of R. So basically, what are the units of R? Maybe we should start there. Oops. So remember, R relates volume, temperature, moles, and pressure. So it has to have the units, so it has to contain all the units for volume, temperature, moles, and pressure. It has to have all 4 of those things in order to relate them.
R is the, wait, let's see. What is the unit? PV, NT.
Let's look at it another way. It seems like everyone's having a problem. Let's go back to, what R is. This should help. Okay. Is everyone seeing a whiteboard, hopefully? Just a big whiteboard?
Yeah.
Okay, cool. So what's, just someone tell me, what's the ideal gas law?
Pivner.
Pivnert, that's right. So how do we write that?
PV equals nRT.
Excellent. So R is what we're looking for, right? R, we want to figure out what's R. So using algebra, how can we isolate R from everybody else?
R equals PV over NT. So you would have to divide, you would have to,
Divide both sides by NT, right?
correct.
Rick, you're on your game today. All right, so I'm going to divide both sides by NT. So I cancel my N's, I cancel my T's, and look what I'm left with. PV divided by NT equals R. So that's what I'm looking for. So basically, I want to plot something that relates PV and NT. Look what's in the numerator and what's in the denominator.
PV.
PV's in the numerator. So is that going to be X or Y?
Mhm.
So remember, Y, that's right. So remember, my slope for
Oh,
M, my
yeah.
slope M of the line is Y over X, right?
Mhm.
That tells me, so if this is X and this is Y, my slope is Y over X. This tells me, since R is equal to PV divided by NT, that if I can plot PV versus NT, the slope of my line will be what?
R.
R. So M is equal to Y divided by X, which is also equal to R, which is also equal to PV divided by NT. So that is what you're going to plot. Okay? So what you're going to do is you're going to have to do some calculating here. And I can help you a little bit, but basically what you're going to be plotting is the original plot you're going to get. The computer is going to draw you a plot of T in degrees C over volume in liters, right? And it'll be like dot, 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 dot. That's what it's going to give you. But that's not going to give you R. So you're going to keep moles constant. That's going to be a constant number, whatever you decide how many moles you're going to use. And P is going to be constant because you're going to decide what pressure you're going to use, either a low pressure or a high pressure. That's also going to be a constant. So that's not going to change. So what you're going to have to do, what you're going to have to figure out is a way to plot PV versus NT. That is what you're going to plot. And so when you plot that, the slope of the line should be R. And obviously I've run this already and you get R. It actually does a really good job. But there's going to be a lot of calculations in it because N is given in grams. We know that's not true. P is given in millimeters of mercury. And we know we don't use that for pressure for R. And T is given in degrees C. And we don't use that for temperature either. So we're going to have to convert that to Kelvin. We're going to need to convert grams to moles. Oops. Get back here. We need to convert grams to moles. moles. And we're going to need to convert millimeters of mercury to what? What unit of pressure are we going to? Atmospheres, exactly. We're going to have to convert that to atmospheres. We're going to have to do a lot of math. The nice thing is you're going to be using either Excel or Google Sheets to do all that math for you. Because it's a pain. It's like sitting with your calculator, punching in all these numbers. You don't have to do that. So basically what we're going to do is plot our, let's go back to, here we go. So when we get our data table, what we're going to do is, where's my drawing? There we go. So our temperature, we can just put down whatever our temperature is in degrees C. So 1, 5, 50, 150, whatever it is. Our volume in liters, that's good. We don't have to do anything with that. We'll take whatever amount of grams of gas, say N2 or something, and we'll convert that to moles. So you can either put grams of gas here and have the computer convert it to moles for you, or you can just convert it to moles yourself and write that in. Pressure should need to be converted to atmospheres. And what are we going to plot? What's going to go on the x-axis and what's going to go on the y-axis?
X is temperature.
What's that?
X is temperature.
It's not just temperature. Because remember, when we plot x over y, or sorry, y over x, we want to get r. And we just determined that PV over NT is equal to R. So what do we want on our x-axis and what do we want on our y-axis?
PV, NT.
Where? Who's x and who's y?
NT is X. PV
That's
and Y
right.
are Y.
So NT will be here. And again, just have the computer do this for you. And y will be PV. And what will our units be? That's the weird thing. What are our units going to be for x? That's why I put a question mark there. Because
Moles
it's important.
over Kelvin.
Nope.
Mm,
You're close. You're very close.
moles times Kelvin.
There you go. Yes, moles Kelvin. So this unit will be moles times Kelvin. And what will the units be for y-axis?
Atmospheres times liters.
That's right. Very good. Yes. This will be in atmosphere liters. So when we plot atmosphere liters over moles Kelvin, that's the unit of R. And so our slope should be R, because that is what relates atmospheres and liters to moles and Kelvin. Okay, so does that make sense to everybody? I know it's a lot to take in, but that's why I sort of said at the beginning, the experiment is real easy to do. The analysis, little trickier, okay? But you'll see that when you set up everything correctly and you have all your units correct, that when you look at the slope of your line, it will equal R. And you should kind of have a faint idea of what R is at this point. What you remember what the numerical value for R approximately? You don't have to have it exactly, but approximately.
0.0082.
Yeah, you should get a slope of around 0.082 or something like that. Something around that. That should be the slope of the line. And remember, Y will be atmosphere liters and X will be moles Kelvin, and that's the unit. So basically what you will have is 0.082 atmosphere liters divided by moles Kelvin. And then when you've got that, ta-da, you've got R. So any questions about how we got to this point? I mean, we did a lot of math, a lot of algebra to get to this point. Is everyone clear on why we have to do all this ridiculous algebra?
Yes.
Really, I'm not sure. I think I got lost somewhere in the middle there. But yeah, that's basically, like I said again, it's all about the units. If you get the units right when you're doing your calculations, if the units all line up, you've probably done the math correctly. So you can trust the numbers in your calculations more if at the end you've crossed out all the things you can cross out and you're left with the proper units that the question's asking. So in this instance, if it's asking for R, then you sort of have to, make sure that your units on the numerator and the denominator sort of line up. And if they do, you probably did it correctly. So your data table, well, basically you can set up your data table however you like. But at the end of it, the last two, like sort of mentioned in the instructions, that if you do an experimental data table, you have to have all the data you collected. I mean, that's the number one thing you have to have. But if there's any manipulation of the data that you had to do in order to get the graph, because next to a data table, we almost always have a graph of that data, right? And if you had to manipulate the data in order to get the graph, you have to show what the data manipulation is. So you can't just show temperature, volume, moles, and pressure, and then have some crazy graph that has all those things kind of mixed together. You have to show what you did. So that's why I had, x-axis. Well, what is it? What is your x-axis? Y-axis, well, what is that? I need to know what it is. So for your x-axis, you're going to have basically NT, and your y-axis is going to be PV. And then then in brackets next to that, what are the units of that? Okay, so that when you show the plot, I'm going to know that the slope of that line is PV divided by NT. Okay, so let's clear this out and just see what the rest of the stuff we have to do. Right, so these are some of the questions you should address during your discussion. We sort of just went over what data we're going to have to plot to get R. We just had a nice long discussion about it. Can you just plot volume versus temperature? So basically, I want you to answer this question. So you're going to make 3 different data tables for the 3 different gases. The last 2 will be, I believe, argon and CO2. And you can pick any, and so there's 5 totals. You can pick the first one, you can have any one you want. The last 2 should be argon and CO2. Basically, sort of what we're asking, is the value of R going to be different? Let me ask you a question right now. Do you think the value of R will be different depending on the gas that we choose?
No.
Okay. Why is that?
Should be constant.
Should be. Is it?
This is a guess.
That's a good guess. My answer is I don't know. I don't know. I've only done nitrogen so far. I don't know if they'll be different, and it wouldn't surprise me if they were. And the reason is, what we're dealing with is something called the ideal gas law. What's an ideal gas? Do you remember from our lecture what an ideal gas is? We haven't really got to what a non-ideal gas is. What's an ideal gas? Other than behaving ideally. Just give any anything that like an ideal gas does or doesn't do.
Ideal gas should be linear.
Yeah, it should. If we plot its all of its value for r, it should be an perfectly straight line. But why? Why is it a perfectly straight line? Basically, what does an ideal gas do or not do that a non-ideal gas? What's different about it? Maybe you don't remember. I didn't go into it in enough detail. But you remember, like a perfect gas or an ideal gas has no interactions with another gas molecule, none. And so when it's whizzing around, it does not interact with another gas whatsoever. And so we sort of mentioned there's no such thing as a really ideal gas, because every gas, every molecule interacts with every other molecule in some way. Maybe it doesn't interact very strongly, but there's some interaction. And so what we may see, and I'm not sure if we'll see it or not, your results will let us know. Some gases are more ideal than others. Some gases are larger than others. And so the fact that they're larger makes them more able to interact with other gas molecules than smaller gas molecules will be. And we'll get to that hopefully in the last chapter. Some molecules are more polar. They're all non-polar, but some are slightly more polar than others. And the more polar you are, the more likely you are to interact with another molecule. And those interactions means that those gases take up slightly less space because they're spending some slight amount of time getting close enough to each other to interact. And when that happens, the distance, the volume between them shrinks. And so their interactions mean that they're not ideal anymore. And so helium is pretty much as close to an ideal gas as we're going to get. It's tiny, and it's super non-polar, and it really doesn't interact with anything. But CO2, as we know, has two polar bonds. I mean, they're opposite to each other, so the whole molecule is non-polar, but there is some polarity in there. It may be that CO2 gives you a slightly different slope than helium will, because CO2 is considered less ideal than helium. But I don't know, because we haven't done the experiments. So I'm kind of looking forward to see if your experiments show that. Don't be surprised if the gases have slightly different slopes, slightly different. It's not going to be huge differences, but they might be slightly different. All right, I probably nattered enough. So who's got a Mac and who's got a PC? So those of you with PCs will probably be able to do the experiment, and those of you on Macs are just going to have to get the data from somebody else. I would suggest going to the chat in Canvas and just asking who's got gas data, and then you can send it back and forth.
I have a Mac, but I was able to open it.
Oh, excellent. Okay. Yeah, basically you go to the site, and it says, it'll give you a little, you need to activate Adobe Flash. And generally, sometimes you just click on it and then there you go. But if you don't have Adobe installed, it'll ask you to install it, and then it's a whole other thing. But at least this time, it's not an applet like our last stupid online lab, which I'm now trying to rewrite to get to do something different. That applet's a nightmare. This isn't an applet. It's a website that runs Flash. So hopefully, yeah, more people will be able to do it. So let's go there. Let's check it out. Oh, share. I want to share something. Where is? Where is it? Oh, try that. All right, so everyone can see this, the website hopefully now? Can you see that? Is that showing up for everyone?
Yep, I can see it.
Okay,
Yeah.
good. So this is when you just open it up, this is the screen you're going to see. And so it basically gives you the choice of what gas you want to use, and you can see they're all going to be different sizes. I guess helium's not one of them. I'm kind of surprised because helium should give you just a perfect line, but these should be pretty good too. I mean, argon should be pretty ideal as well. So we pick a gas. And you can see as I pick different gases, I get different volumes. Why would that be? I thought the volume was just dependent on moles. If I have the same number of moles, how come I'm getting different volumes? Why is that?
Professor, you will choose the pressure and the mass and the temperature. All of these, the three things you will choose by yourself.
Mm-hmm. Yep. But what I'm doing now, you see, I'm just changing look at the volume in my cylinder. As I change the gas, I'm getting different volumes. But why?
Because
Same.
Different mass. And
No, they're all the same mass. They're all 100 milligrams. See, I got 100 milligrams up here.
Is it because they have different molar mass?
There you go. Yeah, they have different molar mass. So if I have the same mass of gas, but one gas is bigger, that's fewer moles of it, right? And so its volume is going to be smaller. And you can see that, like nitrogen has a mass of around 28 grams per mole. So I get that number of liters. But when I pick xenon, which is much bigger, the volume is a lot smaller because that's fewer moles of xenon. So remember that we're going to have to convert a lot of things here to do our plot because our pressure is in millimeters of mercury. We want atmospheres. The mass is in milligrams. We don't even want milligrams. We want grams, and then we want moles. And the temperature is in Celsius. So we have to do a lot of manipulation to get the data we want. So let's just go through how you're going to collect your data, because this part is really easy. You just have to write them down as you're going. So I'm just going to clear the plot here, and I'll select I'll select oxygen. I'll start with oxygen. I'm going to start with a low pressure because I mentioned if you have a really high pressure, those changes in volume are going to be really small. So basically, you're going to have a lot of points really close to each other. And I sort of want to stretch them apart. So I'll pick a low pressure, like I don't know, 220. That's just going to pick that out of the blue. And mass, well, pick a large mass. That'll give me a large volume too. And I'll start with a low pressure, low temperature, go all the way down. And then just hit calculate. So there's my number at the bottom. So it puts the plot, it plots it for you, but you really can't write that down as a number because if you just look at the plot, it's not immediately apparent what those actual numbers are. So what you have to do is make a note. So this you make a note of. So from now on, all the changes in temperature are based on these two things. This is going to be my constant pressure, and this is going to be my constant mass. I'm not going to change those. Why can't I change those? Why can't I change all of them at the same time?
Because we just want to calculate the temperature, so we have to fix the pressure and the volume.
We're not calculating the temperature. We're changing the temperature. So does that make the temperature an independent variable or a dependent variable?
Depends
If we're changing, if the royal we, if we're changing the temperature, does that make it independent or dependent variable?
depending.
No, it makes it independent because shut up. I'm making that choice of temperature independently. Cammy. So the value of the volume is dependent on what I set my temperature, okay? So my temperature is independent because I'm independently choosing a temperature and setting it. And the volume is dependent on whatever the value of the temperature I gave, okay? So why can't I change the pressure and the mass too? I mean, I could, they're right there. I can just slide them all over. Oh, the other thing I want to do is plot my volume versus temperature, right? Plot volume versus temperature. That's what I want to do. Because that's the change we're looking at. We're not changing the mass, we're not changing the pressure, we're changing the temperature. So that's what I'm going to look at. So if I'm looking at at temperature versus volume, why does pressure and mass have to be the same? Everybody's scared or nobody has any idea? Should be scared at this point. So we're just varying temperature and volume. If we vary pressure and mass, are we going to get a straight line?
No.
No, because because if I change the pressure or the mass, then no longer is my new volume dependent solely on the temperature, because I've changed two other things. So when I plot temperature versus volume, I need to know that temperature and volume are the only things changing. That's like the definition of an experiment, right? I have a variable that I'm changing, and I want a variable to change. If anything else is changing, I don't have the relationship between those two things. So if I'm looking at just the relationship of temperature and volume, everything else has to stay the same, or I won't be looking at a relationship of temperature and volume anymore. And that's what we're doing here. We're doing temperature versus volume. So I make a note in my notebook that my pressure is 220 millimeters of mercury. I make a note that my mass is 200 milligrams. And I obviously make a note that I'm dealing with oxygen. That's kind of important. I want to make sure I know what. So I make a note that I'm dealing with oxygen. That should go in my data table. That should be on the top of my data table. Oxygen, pressure equals 220 milligrams mercury. millimeters mercury, mass 200 milligrams, and then all my temperatures and all my volumes. So my first temperature is 1 degree C, and my volume is 0.555 liters. Then I just slide my temperature to another one. Let's say 55. And I just hit calculate. You see, it gives me a new volume this time, and it plots it for me. So my new volume at 55 degrees, so I write down 55, is 0.664. All right, good enough. Then I just pick a new temperature. Say, I don't know, 112. So 112 gives me 0.780 liters. Is that zero significant? The 780? Is that a significant digit?
Yes.
Yeah, it is. It is. It wouldn't be there if it wasn't significant. The zero on the other side, the 0.7, that zero is not significant. That just tells us how big our 780 is, whether it's 0.780 or 7.80 or 78.0. That's all that zero does. It tells us how big the number is. But the 780, that trailing zero, tells me that it's not 779 and it's not 781. It's exactly 780. So I write that one down. I pick a new temperature. Let's say 153. Get another one. So 153 and 0.863 liters up to 199. Remember to hit calculate every time, or it won't give you the point. 0.956. .235 gives me 1.03. And then I'll just put it all the way to the end. So 250 is the max, and 250 gives me 1.06. Okay. So basically, I'm done. I've finished my first experiment. So I take my data and I go to Excel, or I guess most of you will be going to, actually, why don't we do that? We'll do it on Google Sheets. I don't know really how to use Google Sheets, but anyway. So let me clear this out. So Google, I want Sheets. Damn it. Oh, Sheets way down there. Okay. You guys are going to have to help me out with this. All right. Blank sheet. Oops. What the? Oh, for God's sake. All right, going back. If it doesn't let me use Google Sheets, I'll just do it on Excel. Okay, here we go. Yeah, it wants me to put a lock screen on my phone so I can use Google Sheets. I don't know what the hell that has to do with anything. All right, so we should have some information about the data we just collected. So we should have, like, oxygen, and then give the pressure, and that was P equals, what was it, 220 millimeters of mercury. And the oh, mass equals 200 milligrams. So that just tells us this particular set of data it was collected under this particular circumstance. So what data did we collect? We collected temperature and we collected volume, right? And the temperature was in degrees C, and our volume was in liters. So that's fine. So I just type in my degrees C. So I had 1, 55, 112, 153, 199, 235, and 250. And my volumes were 0.555, 0.664, 0.780, 0.863, 0.956, 1.03, and 1.06. So what's the next thing we have to do? So we've got our data in here. So far, so good. This is all the data we collected. What else do we have to do?
You have to convert Celsius to Kelvin.
Yeah, we do. That's a drag, but we got to do it. So here I'll just put T and then K. Because now I don't want degrees C. I want degrees K. Well, not degrees K, just K. Remember, there's no degrees. And so hopefully Google Sheets acts like Excel. We'll see. So I'm going to say equals C6 plus, and what's the conversion to go from Celsius to Kelvin?
273.15.
Yep, 273.15. Oops, 273. There you go. So there's our number. So now we didn't have to do any of that convert. We just let it do it for us. And then we'll get this little dot, this little square on the bottom right-hand corner. And I can just grab it and pull it down. And it's done all the conversions for me. Easy peasy. So my volume, I don't have to do anything with my volume. Volume set, so good to go. What else? What other information do I need so I can put in? What other two things do I need to include in my graph or in my data table anyway?
Moles.
Yeah, that's right. I need moles. So moles O2. Whoops. Mind you. Moles of O2. That's just going to be the same all the way down, right? So how many moles of O2 do I have? And you can have the computer calculate it for you, or that one you can just figure out by yourself. How many moles of O2 do I have? How am I going to figure out how many moles of O2 do I have? It didn't change, right? I kept the same amount all the way through, but how am I going to figure out how many moles of O2 do I have?
You have to get the molar mass of O2.
Yeah, you do. What is the molar mass of O2? Roughly.
15.999 or 16.
You're close. What are you forgetting?
Times 2.
There you go. Yeah, the mole of oxygen, O, is 15.999, but O2 is 2 of them. So it's 15.999 times 2. So what's the mass of oxygen that I have? So look up here. We sort of wrote that in the title. So my pressure is 220 millimeters of mercury and my mass is 200 milligrams. So how am I going to get that into moles?
Do you
You
have to
convert,
Go ahead.
convert
the
100 milligrams to grams?
Okay, how many grams is that? How do I convert milligrams to grams? How many milligrams in a gram?
1,000.
Divide
1,000, right? So I multiply that by 1,000, or do I multiply it by 1/1,000?
1/1000.
Right,
One.
because it's 1 gram on the top and 1,000 milligrams on the bottom. So I multiply by 1/1,000. So how many grams do I have now? So instead of 200 milligrams, I can actually say how many grams. How many grams do I have?
Zero point
0.2
0.2, are you
grams.
done?
0.20.
0.200 grams. There you go. Yeah, so I have 0.200 grams. So how many moles is that?
Is it 0.00625?
Yes, it is. So 0.00625 moles. So basically, I can just put that number in here, and that's it. I'm done. That's like the whole. It's because it's the same number of moles for every bit of data here. So if I do that, will it change it? No, it won't. Good. Sometimes it increases it by 1. So I got my volume, right units. I got my temperature, the right units. I got my moles of gas in the right units. What else do I need?
pressure.
My pressure, that's right. Oop. And what units are going to have for my pressure?
And you need ATM, right?
Atmospheres. So how many atmospheres have I got? Well, basically, what unit am I starting with? I'm starting with 220 millimeters of mercury. How am I going to convert that to atmospheres? How many millimeters of mercury in 1 atmosphere? So I got 220 millimeters of mercury. I need to multiply that by something to get me
1 ATM is
atmospheres. So what do I multiply that by to get me atmospheres?
One ATM equals 760 of those
Yes.
MMs.
That's right. So how am I going to do my conversion? What do I put on the top or what do I put on the bottom?
You put what you want at the top, so ATM goes on the top, 760 go on the bottom. So you would then divide 220 to 760.
Yep, that's right. So 220 divided by 760 That gives me 0.2895 atmospheres. And remember, you can use as many digits here as you like. Use at least 3, but you can use many more. And then when we get to, because I mean, really, there's only two significant digits there, but you can treat it like it's 3. We'll cheat a little bit because we want at least 3 significant digits for R. But yeah, so this is 0.2895 atmospheres for everybody. So that's going to be the same atmospheres for everybody. 0.2895. All right, still not done, because what is it that we have to plot? You remember?
And that would give you your answer.
You have to put all of that in to get the R, right?
Right, there's some combination of these things. Remember, we defined R. So PV is equal to nRT. And then when we moved N and T over to get R, we found that PV divided by NT was going to get us what we're looking for. So what new columns am I going to put in there so that when I plot them, I get R?
Moles times the temperature.
Yes, moles times the temperature. I'm going to put NT here. I'm just going to call it NT because that's what it is. And my unit are moles Kelvin. It sounds kind of weird, but that's what it is. So again, I'm not going to have to do all these calculations because I am stupid and old. I'm going to have the computer do it for me. So equals E6 times F6. So this is my E6. And then the same thing, I just drag it all the way down, and hopefully it'll do all the calculations for me. So far, so good. So that is N times T. And like, remember, the units, hold on to those units, because that's the only way you're going to know you're doing this thing right. What she got? Oh, she's after a bug. Oh, could you put that back on the, I think the modem fell over. Yeah, so we keep our units. What's the next one we need to do? So we've done NT. What's the next thing we need to do?
PV.
PV. And that's going to be, what are my units of PV going to be?
PV is basically pressure, volume.
What are my units though?
It's grams times.
Grams. Where the hell are you getting grams from?
Actually, I'm tripping.
Yeah, you are. PV. So what are my units for PV?
Atmosphere times liters.
There you go. Atmosphere liters, pressure and volume. So, not in your car, are you, Rick? You're not driving, I hope.
Multitasking.
All right. So we just do the same thing here. Just multiply one column by another column, so you don't have to do all this by hand, which is kind of nice. So we do atmospheres are G6, right? So G6 multiplied. And it's just the star or asterisk for multiplication. Oh, I didn't do equals. Oops. Equals. There we go. G6 times our volume is at D6. D6. And just hit enter. So then we just drag it down. It does all the work for us. Oops. Right, but the wrong way. There we go. And we trust and hope and pray that we'd set that up properly. We should know if, when we plot this all out, we get some bizarre plot that doesn't give us anything, we'll know we set it up incorrectly. But hoping this is right. Okay, so now what are we going to plot? Candy, leave the bugs alone. Not bothering you. What are we going to plot here?
The X and Y axis.
Who's X and who's Y? Oh, I shouldn't have taken down my little drawing there.
Temperature. Concentration.
So R is equal to PV over NT. So what's going to be my x-axis and what's going to be my y-axis?
X is NT.
That's right.
Oh, yeah, that's right.
That's x, and my y is going to be PV. Because R is equal to PV divided by NT, which is equal to y divided by x, which is equal to the slope of the line. So if we plot this versus this, fingers crossed, we're going to get the slope that will equal R. So let's do that. Wait, see if I remember how to do this. All right, so I think we select our two. So the one we select first, I think, should be X, hopefully, and the one we select second should be Y. I'm hoping, praying. Okay, I go to insert, right? Chart. And hopefully it'll pop up with something in a year or two. There we go. I want a scatter chart. What else do I want? Oh, customize. There's my chart. Looks good so far. Customize. Series. I want the equation. Trend line. That will put a line through all those points. So far, so good. Now I want the equation. They'll show me the R squared. That tells me it's a really good line. That's good to know. Where do I get the actual grid lines? Where's my show the equation? Anyone remember where I get that? Is that under series?
Label. On top of show R squared.
Oh, label. Where's label?
It's on top of R squared.
I don't know what that means.
In series, sorry.
Oh, series. Oh, then here. Oh, above it, data labels. Oh, thank you. Nope, that just tells us what the units are. Oh, legend? Nope.
Oh, you just passed it.
Oh, where was it? Oh, grid lines and ticks? Nope. God damn it. It should be much easier to find.
It was in series.
It was in series. Series. Okay. And it's hidden somewhere, because who would actually want to see what the slope of their line is? Where? Oh, number format. Is that it? Nope.
No.
Nope, I don't want that.
It's near the bottom.
Where?
It says label,
Oh,
custom.
label. Label. There it is. Use equation. Oh my God. There we go. And let's have a look. So our slope. So we got a really good line. I mean, obviously, you know, the line goes completely through it. My R squared is 1, meaning that every single point is directly on that line. And we've got a slope of PV versus NT. So that should give us R. What's the slope of my line here?
Zero 0.094.
Right. So my slope is right there. So that tells me the relationship between Y and X, which is the slope, which is R, is 0.094. And we were hoping for 0.82, right? That's sort of what we were shooting for. So it's a little off. Now, I need to go back and see if I've made any mistakes or whether oxygen just is maybe one of the non-ideal gases. So I'll go back and I'll check all my numbers, make sure I did them properly. But this is pretty close to what we're looking for. So I don't know, I may have punched in some numbers wrong or something like that. But the fact that everything's on a perfectly straight line kind of tells me that that's probably right. So that's how we would find the value for R. Now remember, that is just for oxygen and just at that pressure. And just that amount. If I change any of those things, I'll get a different line. Hopefully the slope will be the same. I won't know that for sure until I do the experiment. But so does everyone see how we got here? Should we do one more and go through it again?
Professor, could you just show me how you get the equation for the slope? How you get the value of the slope?
Oh, okay. So that was under series. So we hit series, and we scroll down, and trend line. You click on trend line. That will fit. So it takes all the points that you've plotted, and it'll fit a straight line through them. And then when you want to see what it is, you go down to label and select show the equation or use equation, and it'll plot that for you.
Okay,
It'll give you the slope.
got you.
So what's this other number that's here? So we got two numbers on the equation. What's the other number?
R,
So we've got 0.094, and what's this plus minus 4.61 times 10 to the minus 4? What's that?
It's R squared.
Nope. No, the R squared is 1. That's a separate number over there. I'm talking about this one right here. What is that? When you fit
Uncertainty.
B.
Nope, it's B. That's right. B. Remember, when you fit a straight line, you get Y equals mx plus B. And what does B represent? What is B? Anyone remember? I'll put it this way. If you had a perfect line that went right through 0,
B is the y-intercept.
there you go. Yeah, so if you had a perfect line that went right through 0, the slope of the line would just be y equals mx. But if it doesn't go through 0, it goes through the y-axis at some point that isn't 0, either above 0 or below 0. So this tells us that it goes through the line slightly below 0 at negative 4.61 times 10 to the minus 4, which is a tiny number. When you're looking at, you look at the the values of Y that we've got over there, that is really small. So that's basically 0. So that also tells us that we probably did it right, because ideally it should just go right through 0, because at no moles of gas at 0 temperature, we shouldn't have any pressure or any volume. Everything should be 0, at absolute 0. That's what moles times K would be, right? It would be 0. So it should go through 0, and it pretty much does. So I think we did this one right. And so oxygen may be a little different than the rest, but we'll see. Maybe when you do it, or we can do it again, maybe with different amounts, and see if we get a different answer. Should we maybe do that? Just to check on our work. That sound like a good idea?
Yep.
That's the spirit. That's the spirit. Yeah, so we can either do oxygen again and see if we get the same slope, or we can try a different gas.
Can we
You-
try different gas?
Sure, do a different gas. Dix, I will show you real quickly that I did this with nitrogen last night. But where? Oh, here it is. So I did this with nitrogen last night, and you can see that when I plotted it, I got 0.0822, which is pretty much exactly R. So that told me that, hey, I can do this right. So nitrogen should give us like hopefully, it did for me last night anyway. Maybe it's all screwed up today. The atmospheric pressure is weird today or something. So it worked for that amount of nitrogen. So we can let's try a different gas.
So, Professor, just a quick question. We don't have to start from 0, the line. It's not necessarily to start the...
Well, you didn't collect a data point at 0.
Okay.
You weren't given the ability to have a temperature of 0. Right? I mean, the lowest temperature was 1 degree Celsius, which is 274. So it doesn't allow you to go all the way to absolute 0. So there's no way you could put a data point there. So don't worry that you didn't put a data point there, because that's impossible. And you shouldn't, because you can't assume that that's what you're going to get. All right, so let's go back to our gas law. So hopefully everyone can see the gas law screen again.
Mm-hmm.
All right, so it's clear. So we want to pick a different gas, right? We want to pick something different. Is that the consensus?
Can do AR.
Yeah, we can do any of them. It doesn't really matter. Let's do argon. And hopefully argon will.
I have a quick.
Sure. Yep.
So for the lab report, there's just like total of 3 gases.
Yeah, so you should have 3 different data tables and 3 different plots. Yeah. It
So
should be three different gases, 3 different pressures, 3 different masses.
So the first one we can choose, and then the other 2 are xenon and carbon dioxide, right?
Yeah.
Okay.
Yeah. Yeah. So let's pick argon. Let's lower our pressure down to 123. It looks like fun. And start at a super low. Actually, let's change the mass to 151. Yeah, that's pretty random. All right. So start at 1 degree and calculate. All right, so argon, this time. So at 1 degree, I've got 0.525 liters. Okay, go up a little bit more, 41. So at 41, I've got 0.602. Then at 95, I've got 0.705. 136, I've got, oh, forgot to hit calculate. 0.784. 181, I've got, oh, calculate again. 0.870. 216. I've got 0.937. Then at 250, I got exactly 1. Okay. So I've written all this down. And I made a note of my pressure was. I made a note of what the mass was. So let me go back to my spreadsheet page. If I can move this out of the way. Put that there. And just move over. Can I just move over? There we go. So basically set up the same thing, only this time with argon. So this time I've got argon. I've got 123 millimeters of mercury. And I've got 151 milligrams of gas. I have changed the temperature. In degrees C. And I've collected volume in liters. Right, then I just put them in there. So 155, 112, 153, 199, 235, 250. And then my volumes were 0.555, 0.664, 0.78, 0.863. It doesn't matter if you put the 0 in there, the computer just takes it out anyway. So even though that 0.780, that 0 is significant, the computer ignores it. So it doesn't really matter the calculations anyway. 0.956. Oops. 1.03. Oh, wait a minute. No, that's not right. Oh man, I'm putting the wrong numbers in. Damn it. Let's put them in from the last experiment. Oops. 0.525. There we go. That's an easy mistake you're probably going to make. I just did it. You're collecting all this data. You're going to have a whole big page full of numbers. Just make sure you keep them separate. Oh, 87. 82 or 87? Yeah. 7, I think. 0.937 and 1. Okay. So we do the same thing did before. We need to change our temperature to Kelvin. Oh man. All right, so I'm going to add J6. And what's my, oh, JG. What's my conversion again from Celsius to Kelvin?
273.15.
There you go. And then just drag down, so that's all done for me. Nice. My volume's good. I need to calculate moles, right? So I need moles of argon. Someone want to do that one for me? I also need the pressure in atmospheres. Someone give me the pressure in atmospheres. Someone give me the moles of argon. So we got 123 millimeters of mercury. I need someone to convert that to atmospheres, and I've got 151 milligrams of argon. I need someone to convert that to moles. Whoever gets there first. I mean, you're gonna make me use my own calculator. That's just sad. Come on. How many moles of argon do I have? I have 151 milligrams. How many grams of that? How many grams is that? How many moles is that? Someone's got to have a periodic table in front of them. Good Lord. This is bad, people. I'm reaching for my own periodic table. Come on. Don't make me do this.
One 51 milligrams is 0.151 grams.
Excellent. Oh, atmospheres, you mean?
No, argon, moles of argon.
Oh, yes, yes. That's not mole, that's grams. Okay, you're halfway home. How many moles is that?
0.003779991.
Right, so 0.0037.
7
Keep going.
7991.
0.0377791.
91.
377. What am I missing here? I have 37791. What should it be?
There should be 2 nines.
2 nines. And then a 1.
Yes.
Okay, excellent. We're counting on you, or else if we get this slope wrong, it's going to be all your fault. No, your fault.
Oh no. Please check.
I can't. All right, I'll check. Anyway, pressure. What's my pressure? Yep, 377991. You are perfect. Yes. What's my pressure?
Pressure
Isn't it the same?
Mm-mm.
point.
No, last time we did it, it was 200. Oh, wait a minute. Last time we did it, it was 220 millimeters of mercury. Now it's 123. So it's different pressure. What's our new pressure?
After doing the calculation, 1, 2, 3, and you divide that by.
The pressure is going to be 0.16184211.
There you go. Okay, so that's our pressure in atmospheres. That's key. How did you get that number? How did you get that?
You divide it by 760.
You don't divide. You multiply by 1
yeah,
over
yeah.
760. There you
Sorry,
go.
yeah.
Never divide, ever. Okay, so I think we got all our, looks like we got all our ducks in a row here. So remember, because of our good friend Pivner, we want to, N is going to equal PV divided by NT. So we want to plot NT versus PV, X over Y. So my NT is going to be moles times temperature. So I got my moles here and I got my temperature here. So for NT, and remember, always have the units. If you have a data table, it must have units in it. You can't have temperature and then give a whole bunch of numbers, because nobody knows what that means. Is that Fahrenheit, Celsius, Kelvin? Don't, you know, some temperature you just made up. So we don't know. So we always give moles Kelvin for if we're dealing with moles and temperature. And that is just going to be multiplying our L6 times our M6. M6. So, and we just drag that all the way down. Okay. And then on the top, we want PIV. So we want PV here. What's our units for PV?
Atmospheres and years.
Someone's been busted. I don't know who that was. They've been busted though. So what's my units for PV?
Atmospheres times liters.
Right. That is correct. So again, I just multiply one column by another column. So my columns are P is in N. We start with N6. And my liters, my volume is in K6. K6 is the first one. There's my PV. Drag that down. All right, so it seems like I got everything I need. I got my NT and I got my PV. So let's start over again, and then we'll compare the two. Let's compare the two. See if we get something different. So drag what I want. Go to insert again. I want a chart. I want. Now, why didn't it just give me a scatter like I wanted? Okay, scatter. And I want to customize it. My series. I want the trend line. Show the R squared. Oh, we got a point off the line here a little bit. Interesting. And damn it, where did the
Label.
label? That's right, label. Thank you. Use equation. Ooh, nice. All right, so
Professor, just I notice you click on show R square. Why?
I'm interested to see if they all fall on the line or not.
Okay.
Yeah. So we see here that one of them's off. The rest seem to be on the line. The last one, the largest one, doesn't. And that is at the highest temperature. So it's this point here. Oh, actually, I could put the data up if I want to, but that's, yeah, it's that point there, which is the highest temperature. Interesting. So, but let's look at what our R is. And we can also take that point out if I may have made a mistake, writing that number down. I don't think I did, but I might have. So, or argon may vary from its ideal nature at high temperatures. Generally, it's at low temperatures, but who knows? So, what is our slope? What's the slope?
0.0801.
That's right. So our slope is right there. Because that tells me that our y which is, oh, I didn't put the labels on. I put the labels on. So we know that Y is PV. It should have PV. I'll put the labels on there. And X is NT. And so my slope is PV divided by NT, and that equals R. And it is 0.0801, which is pretty close. That's not bad. I mean, that is really close to 0.0821. That's really close. So I'd say that's pretty good. And I think it's closer than our other one. What was our other one? Was 0.094. Yeah, that was much different. So yeah, I'd consider that a win. 0.0801. But like I said, when I ran it for nitrogen, I got exactly the right answer. So it may be you're going to get different values of R every time. So that's kind of cool. The other thing you can do is if you get that value, so if we get this value for this amount of argon at a particular pressure, change the amount, change the pressure, run it again, and see if you get the same value of R, okay? So it looks like you may or may not get exactly the value of R. You're gonna get close. So do all three, and then in your discussion, discuss why they could be different.
Professor, just I want to ask you for the data when I choose the temperature in the beginning, do I need to use the same temperature that I use for the first gas, the same to be the second gas? And
No, doesn't matter what the temperature is. Make it any temperature you want. That's the whole point, is that, you know, since R is supposed to relate all the pressures and all the volumes and all the amounts of moles and all the temperatures, it doesn't matter. It shouldn't matter what value you choose. The only thing that matters when you're doing this is make sure when you're varying temperature and seeing its effect on volume, don't change the pressure and don't change the amount. Keep it the same for one whole trial. Then you can change them, and you'll see you'll get different values. But your slope of your line should be approximately the same.
And how
Yes.
many points I have to do? I
said at least 6, but okay, you can do more if you want, because really it doesn't matter. I mean, hell, you saw it's just as easy to do 15 as it is to do 6, because when you have the computer doing all the calculations for you. The work isn't in the calculations. The computer will do it. The work isn't getting it set up properly. So once you got it set up properly, you can just run through, like, you know, hundreds of these. But I'd like at least 6.
And in the table, I should include all the digit number here?
Yeah, just copy and paste this table.
Okay.
Yeah, I mean, if you want, you can go through and limit the amount of significant digits in the table, but you know, if you don't know how to do that, I don't really care. All right, so go ahead.
Just
in the discussion, what I have to discuss in the discussion, what I have to compare these 3 gases?
Well, read the, have you read it? Yeah, just read it, and it'll tell you what you need. In any discussion, you have to, just basically discuss your results. You know, did you get close to the value of R? Why or why not? Do the 3 gases have different values of R? Why might that be? Yeah, that's that sort of thing.
So, Professor, we can just copy paste the table that we are doing right now into the.
Oh, hell yeah. Oh, yeah, don't write it down. My God, that's insane. Yeah, I mean, you went through all the trouble of, typing all that in and getting a really nice computer graph. Yeah, don't do that. Oh, one thing I will point out though is notice on the left, my graph on the left here, it's got all the information I'm really looking for. I have a nice, I'm saying what it is I'm plotting. I have my axis labeled. All that is excellent. I have my equation. The one on the right, I don't have the axis labeled. I don't have a title. So this would be worth less. The one on the right would be worth less grading than the one on the one on the left, because you have to have your axes labeled. That's incredibly important, because a graph without axis label is basically like a group of data without any units. It's meaningless. It's just a bunch of numbers. Oh yeah, wow, there's a relationship between these random numbers. That doesn't tell me anything. So you have to have the axis label. I think where that was where you just right click, chart and axis titles. Yeah, give it a chart title and you just type it in and give it axis. So this would be, argon, and you could even give the pressures, and then say you're plotting PV versus NT. Where's my, okay, and then, yeah, so just right click and say the axis titles you want. Your horizontal axis title will be NT, moles Kelvin. And the vertical axis title will be PV atmosphere liters. Oops, atmosphere liters. There we go. There you go. Yeah, you have to have them labeled, or else it's basically a worthless diagram without labels on them, because we don't know what it represents. All that tells us is that this set of numbers matches this set of numbers. That's not useful information. Right. So that, yeah, Dr. Gagreb he helped me edit this last night, and he was very insistent that the labels, the axis that be labeled. And I agree with him. So I put it in the instructions. Anybody have any other anything else you want to ask?
For the table, should we put it into 3 sig figs or just
if you want? It's not necessary. I mean, so it'll be fairly obvious, the numbers that you typed in and the numbers that the computer calculated for you. I mean, so yeah, so it's not that essential.
Okay.
No, if you want to, that's fine. But I don't really care. So that would be under format, I guess, like numbers, and that gives you, is one of them custom number format? Oh, so yeah. So what? You just tell it here, like how many significant digits, something like that. I don't know how to use. I haven't used this particular version, so.
When you click X on that thing, right beside the 100% on the page itself, it'll say decimal places to the right or to the left.
Oh, here.
Yeah.
Oh, decrease decimal place. Okay, that's easy enough. Yeah, so if you want to like click on those and change them to, fewer decimal places. I guess that's fine. It doesn't really matter though. I mean,
Okay.
But no, it's pretty easy to do, and it would make your data table a little neater. So yeah, sure. Yeah, I would have at least, and I don't think that affects the calculations, right? I think that just the computer will still keep all those numbers that, but it just won't show them. I'm not sure if that's correct.
When you decrease the decimal place, it just rounds off.
Yeah, but it doesn't round off for the calculation, I don't think. I'm not sure. I can't bet on that, but yeah, it shouldn't matter too much because really you're only getting 3 significant digits for your slope anyway. And on the one on the left, we only got 2. So there's probably some way to get more digits out of there. I'm just not sure. If we click on it, can we get more digits out of it?
I think it's to be more safe, just copy all these numbers.
No, it didn't say anything about increasing the digits. No. Yeah, I'll try and if I find a way to so you can get more significant digits from the slope, I'll send you a note. Right now, I'm not. If anyone knows how to do that, would you share that information with us? I'm more of an Excel hater than a Google hater. All right. Anything else? Any other
Yes.
questions? Yeah. Go ahead.
Did I pass my exam?
I think we'll take that offline.
You could just say it in front of the whole class. I'm not.
I haven't graded it.
I'm just fine. Okay.
Yeah.
Just to be clear, Professor, for this lab assignment, we will include the 3 graphs and the 3
Yes.
data.
Yeah. 3 data tables and a graph for each one. Yep. Yeah. And if anyone figures out how to get us more than 2 or 3 digits on our slope, well, I guess that just means 0.0940, I guess, since we have 3 significant digits on the right and only 2 significant digits on the left. We could probably make that assumption, but I'm not sure why there'd be a difference.
Another question, do I need to include in the lab report how I calculate the NT, how I calculate these numbers, or no, as long as I did correctly in that?
Well, you should discuss why you did that.
Okay.
I mean, that's part of the procedure. You know, why, you know, I did this, to sort of explain, well, why'd you do that? Yeah, you can either have it in the procedure or in the discussion. Either way, just have it mentioned somewhere. All right, anybody else got anything? Or should we wrap it up and we'll see you at 4:15? We'll finish chapter 8 tonight, and we probably will start chapter 9. I included, I did a lot of work on Canvas this morning. I put slides for chapter 9 up. I put all the, usually I have lecture questions and then the answers are blocked out when we're doing lectures. I put all the answers, the questions and answers up for all the chapters. I put that in a separate place in its own module, and something else. I'll think of it later. But yeah, that's what we'll be doing tonight.
Sounds good.
All right. Anything else before we go?
No.
All right. I will see you in a little while. And as usual, yeah. Any question? I've got office hours tomorrow. If you're having trouble with this lab, yeah, there's a lot of calculations, so you're gonna be spending a lot of time playing with the computer. Sorry about that, but we're getting good results, I think. So I'm gonna do a couple more, see if I get the same thing. Anyway,
Nice.
all right. I'll talk to you soon. See you in a little while.